Okay, so today I'm going to teach you how to calculate the height of tide at any time. So we'll use just a regular piece of paper, and then we're going to use the 1983 tide tables, which is our testing material for the Coast Guard exam. And I've set up an example question here. What is the height of tide at 1500 in zone description +5 at Jacksonboro on February 18, 1983. Everything is in 1983. That's what the tide book is in. So what I'll do first is explain to you how to use this publication. All right, this has the tidal tables from 1983, and there's 4 sections in this publication. The first section, well, there's more than 4. There's 4 we're going to use right now. The first section is tables that look like this. This is called Table 1. They look like calendar pages. So this tells me that at Eastport, Maine in 1983, right, on February 1st, which happened to be a Tuesday, February 16th happened to be a Wednesday, okay, but on the 1st, on a Tuesday, at 01:05, the height of tide, so the height of tide above the charted depth, is 20.2 feet, or 6.2 meters. We're not going to use the meters for this example because our questions operate in feet. Right, so we'll use this time and this height, and these are large stations. So these are reference stations that we find in Table 1, or harmonic stations, okay? So what does this time mean? Well, if we look at the bottom of the page, it tells us that this time is for a meridian of 75 degrees west. So I know, because I divide 75 by 15 degrees per zone description, okay, that 75 degrees west longitude is observing zone description +5. So I'm not observing daylight savings time, right? So these are all in +5, and as long as my problem is given to me in +5, I can just pull the times out of this and work my way through the problem, right? So this is what the first table is. We have pages January, February, March, and we come over here, we have April, May, June, July. It would be a huge book if this was for every single station ever. So in order to minimize, we use subordinate stations that reference our reference stations. So Table 2, okay, tidal differences and other constants. Table 2 is corrections for subordinate stations. So here, if you were trying to find the height of tide at Cartwright Harbor, okay, maybe you should verify the Latin long, okay, you'd be able to correct the high water time by a -3 minutes, the low water time by a -34 minutes, the high water height in feet by a -1.3 feet, and the low water height in feet by a -0.6 feet, right? For our future problems, we'll use the mean range of tide, okay? But for here, or the mean tide level, mean range, we don't need to use that for a basic question like the one that we're working on right now. What are these corrections corrected on? They're corrected on the Table 1 reference stations. How do I know what reference station to use for Cartwright Harbor? I scan up and I see Cartwright Harbor is based on Halifax, and that is on page 20. So that is my reference station, right? The third table in this publication that we're going to use is Table 3, the height of tide at any time. This is an explanation of how to use it. It's great. If you ever forget, read the explanation. But this is the table that we're going to work through primarily today. Okay, and if we can find 3 of the 4 inputs into this table, we'll be able to pull out the 4th one and give you the height of tide at any time. So here, the top input says time from nearest high or low water. This says duration of rise or fall. This is range of tide, and this is correction to height. So we'll be working with table 3 as we go through this. And I told you there was 4 sections. Yes, there are many other smaller sections in this publication that we're not going to use. But the 4th one that we will use is the index. So let's start there. The index, in the index, I'm going to look up Jacksonboro, South Carolina. Okay, so here is Jacksonboro. Right here. And I see a number listed 2645 by it. I know, because I've done this before, that this is the reference number to enter in table 2, right? This is a subordinate station because it doesn't have an asterisk by it like this. Okay, in Venezuela, this one is a reference station. I can go directly to page 152. I don't need to go into table 2. Page 152, I'll find I'm in table 1 with daily predictions. Okay, but in Jacksonboro, I don't have that asterisk. I don't have a page number, so I'm going to just go straight into table 2 and to 2645. Okay, 2645 Jacksonboro here at the bottom. Might be helpful to be able to see the top of the table here. And for that reason, I'll try to keep it in sight as I work through this problem, right? So I'm going to use the way that this table is set up to structure my own excerpts for the table that I can use to calculate the answer to this problem. So we're working here with Jacksonboro. That's a reference station. Okay. I mean, that's a subordinate station. We're going to have to go to a reference station. What's the reference station for Jacksonboro? It's on the Savannah River entrance, which is on page 100. Okay. So here, every time I receive a height of tide at any time problem, I'm going to set up the following table. I set up table 1, which is my reference station. In this case, I know it's Savannah River entrance, okay, on page 100. And then I'm going to set up table 2, okay, which is my subordinate station corrections. And then when I apply my subordinate station corrections to my reference station daily predictions, I will get out my subordinate station height of tide. Right? Okay, in my table 2, I'm using the reference number 2645. So it can be handy to just note that there. Now, as we can see from this structure, I have differences. Differences from what? From the reference station. Okay, differences are in time and height. And they start with time for high water and low water, and then height for high water and low water. So I'm going to make this exact same table right over here. So I have time for high water and low water, and then I have height, and this is in feet, right, for high water and low water. I'm in table 2 now, so I might as well work with what I have before I get into table 1. So I'm going to pull out the figures and put them along this line for table 2. For the time of high water, I will add 3 hours and 16 minutes to the reference station time, and that'll be when the time of high water happens. So I'm adding 03, because 3 hours and 16 minutes to the high water. For the low water, I'm adding 0421, okay, 421, 4 hours and 21. For the height of tide in feet, I'm going to multiply 0.28. This is an abnormal question. So this example is giving you something that you won't come across too often, right? Except for in my next example. Okay, here you have negative, here you have positive. Usually it's a plus or minus in tide, but occasionally there'll be an asterisk, and that'll reference that you multiplied this correction. So we're going to multiply 0.28, and we'll multiply 0.28 for the low water height as well. Okay, that's all I need from this table 2 at this time. So where do I go? I go to page 100 and I look up in table 1, the Savannah River entrance. Okay. So this is just excerpts from the 1983 tides. It won't have every single page. We skip around quite a bit. Okay. So here we are at page 100. This is the Savannah River entrance. I'm looking for February 18th. So here's January, here's February. I scanned down to February 18th. Happened to be a Friday. And I'm looking for the height of tide at 1500. So here I have to start figuring out what my end result is. What I'm going to be doing is using table 3 to interpolate, tabular interpolation, between the high and low water times that are before and after 1500 to get the actual height at 1500. So I need my subordinate station height of tides for high and low water to end up being, after the correction is applied, before and after 1500. This is a pretty large correction, so I should take that into account as I'm picking out times. If I have to add, 3 hours to the high water, this is a high water. How do I know that? Because the height is 6.2, and the one before it, the height was 0, and the one after it, the event after it, is a negative 0.1. So those are 2 low waters, and this is a high water. So this is 11, 12, 13, 14. That gets me pretty close. So I usually shoot for whatever time would get me closest to 1500. So I'll choose 1121, and I'm going to choose it for the high water because I decided that it was a high water event. So at 1121, the corresponding height at the reference station is 6.2 feet. Okay, so 1121, I add down 21 plus 16. I could do it in my head, but I'll do it on the calculator. Okay, 37. And then 11 plus 3, 14. So 1437 is the time for the high water at Jacksonboro, South Carolina, okay, on February 18th. So this time ended up being before 1500. Because it's before 1500 and I know I have to interpolate, I'm going to locate a time that's after 1500 now. So the next event is at 1749. It's a low water event. Okay, so 1749 plus 421. I take 49 plus 21. That's 70, so I subtract 60 out of that. That gives me 1 hour and 10 minutes. Now I have 17, 18, 19, 20, 21, 22, so I have 2210 is the low water time. Is this before and after 1500? Yes, perfect. I can move forward. Now because I'm here, I will get the height of the high water, which is 6.2 times 0.28. which is 1.7 feet. And then 0.28 times 0.1, and I can put a negative on there, sure. And that gives me a negative 0.0, right? So the height of tide at Jackson Borough for the high water that occurred at 1437 is 1.7 feet. Okay, the height of tide is the height above the charted depth. And for the low water, the height of the water is what the charted depth says. There's no correction to be added, right? That's what that's telling us. But we don't need those numbers. We need 1500. So we're going to enter table 3. Table 3 is just one page. And it allows us to calculate the height of tide at any time. So here we need the time from the nearest high or low water, the duration of rise or fall, the range of tide, and the correction to height. Well, I know I can find the duration of rise or fall easily because at 1437 there was a high water, and then at 2210 there was a low water. So at 1500 the water is falling. And what's the duration of that? Let's find out. Duration of fall is 2210 minus 1437. When you're working with times, you don't ever want to type in times to your calculator, right? So I'm going to take 10, I'm going to minus 37, so I have to borrow. I have 21 hours, 70 minutes. I take 70, I subtract 37. That gives me 33 minutes. And then I have 21, I subtract 14, and that gives me 7 hours. So I have 7 hours and 33 minutes for my duration of fall. For the range of tide, in feet, right, because we're working with feet here, I take the difference between the high water and the low water. So here I have 1.7 feet and 0.0 feet, and the difference between those is 1.7 feet. The time from nearest high or low water I have to determine by comparing the desired time of 1500, right, with each of the times for the events, and whichever is closer, that's the time I'll be working with for my interpolation. So I take 1500 and I see how close is it to 1437. And then I take 2210 and I say how close is that to 1500. Here I'm going to borrow again. This makes 14 and this gives 60. So 60 minus 37 is 23. And that's 0. So 0 hours and 23 minutes. That looks like the closest one, but for the sake of argument, we're going to work out the other one. So 10 minus 0 is 10, and then 22 minus 15 is going to be 7. So 7 hours and 10 minutes is definitely larger than 22. That tells me that the high water is the event that's nearest to the desired time. So I do not need this. Okay, I do not need this, and I'm not going to work with this. I know that I'm going to base my interpolation off of the closest time and its corresponding height. High water is what I'm comparing my table information to. So we have 3 entries into this table, so we can work through it. The duration of rise or fall is 7 hours and 33 minutes. Here you see 7:20 and you see 7:40. You just choose whichever is closest. So we're going to go with 7:40. We'll scan across until we find a time that is closest to 23 minutes. All right, so let's work our way back here. 23 minutes is closest to it's even, right? So it's even between 50 and 31. So I can either choose the largest or I'll just work between both tables, okay? So I'll choose both these columns. Usually I would just pick one column, okay? Then I'm gonna scan down here until I find the range of tide on this left-hand side. The range of tide is 1.7, right? So I find 1.5. There's 1, 1.5, and 2, so I'm closest to 1.5. And in the columns that I found, I have the correction to height of 0 in both columns. So that worked itself right out. Okay, so my correction to height is 0. 0.0 feet, right? So what do I do with this correction to height? Well, because it's 0, I don't do much, right? But I still need to know what the height of tide is at 1500. So I don't really know. It's not 0. That's a correction to height. So what I'm going to do is go back to the nearest event. The nearest event was high water. So when I did my tabular interpolation, I was referencing this event. So this correction to height is a reference to this height. So I take 1.7 and I apply the correction to height of 0.0. Does that mean I add or subtract it? Well, I have to end up in between these two figures, right? 1500 is in between 1437 and 2210. So I need the height to be in between 1.7 and 0. So in this case, I don't have to make a decision. It's just 0. But had this been a correction to height of, say, 0.2, I would have to subtract it because I can't be higher than the high water. I have to be somewhere in between the high and low at 1500. I've already determined that the water is going down. The height of tide is decreasing. So I would subtract it. And I end up with 1.7 feet at Jackson Borough on February 18th, 1983. And this is the answer to my problem, 1.7 feet. All right, so that's how we do our height of tide at any time calculations. And if you need any more description on the question or on exactly the figures I wrote down here, I will put them in the notes. Thank you.